Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. Solvolysis of tertiary benzylic chlorides proceeds via SN1 mechanism. The rate depends on the stability of the carbocation intermediate formed after loss of Cl. Greater stabilization of the carbocation leads to faster solvolysis. Moving on to the next step. Identify the carbocation formed in each case. All three compounds form a tertiary benzylic carbocation, positive charge on carbon bearing to methyl groups and an aryl group. The aryl ring can stabilize the carbocation through resonance, delocalization of positive charge into the ring. Moving on to the next step. Assess additional stabilization from substituents on the ring. Compound 3, cumyl chloride, unsubstituted phenyl baseline tertiary benzylic carbocation stability. Compound I, para-cyclopropyl group on the phenyl ring. The cyclopropyl group at the para position is a powerful electron-donating group through homoconjugation bisected cyclopropane orbital interaction. It donates electron density into the ring via resonance, stabilizing the positive charge on the benzylic carbon. This makes the carbocation more stable than in 3. Compound 2, para-cyclopropyl plus orthomethyl on the phenyl ring. The orthomethyl group causes steric hindrance, steric inhibition of resonance ortho effect, which forces the CH3 to Cl group slightly out of plane with the ring, reducing the conjugation between the carbocation and the ring. However, the para-cyclopropyl group still provides stabilization. Net effect: the orthomethyl group reduces the planarity conjugation somewhat compared to compound I, but the para-cyclopropyl group still provides more stabilization than the unsubstituted phenyl in 3. Additionally, the methyl group is electron donating by induction, which can also help. The key point often tested is that the orthomethyl group introduces steric strain that slightly twists the ring, reducing resonance stabilization compared to I, but to still benefits from both the cyclopropyl and methyl electron donation. Weight re-evaluating for answer D to I3. Compound 2 has both a para-cyclopropyl group and an orthomethyl group. The orthomethyl group is electron donating by hyperconjugation induction, adding to the overall electron density donation into the ring. Even with slight steric effects, the combination of para-cyclopropyl plus orthomethyl makes compound 2's carbocation the most stable. Compound I has only the para-cyclopropyl group, making its carbocation more stable than 3 but less than 2. Compound 3 has only the unsubstituted phenyl, providing the least stabilization. And for the final step, most reactive, 2 para-cyclopropyl plus orthomethyl is equal to maximum carbocation stabilization. Second, I, para-cyclopropyl only. Least reactive, 3, unsubstituted phenyl. Order 2I3. Why other options fail? A. To 3I, incorrect because para-cyclopropyl in I stabilize more than unsubstituted phenyl in 3. B. I to 3, incorrect because 2 has additional methyl donation making it more reactive than I. C. 3 to I, completely incorrect, electron donating substituents increase rate, not decrease. Therefore, the correct answer is D. Therefore, the correct answer is option D.